Hey guys, thank you so much for watching this video. This is going to be the lecture for today, Friday, and this is going to cover a bit more of the expanded octets and some of the exceptions to the octet rule in terms of Lewis structures, as well as resonance. And I'm going to draw every single molecular geometry that you need to know. So there's some of the stuff is in your notes packet that I gave you, so make sure that you pay attention so you're not writing too much. But this is the last slide we left off on, which was the formal charge. The value of formal charge is to help you determine which is the best Lewis structure. Now, we can write a lot of Lewis structures, but sometimes they're drawn correctly because they have the correct number of valence electrons on them, but sometimes the model is a little bit more unstable due to the charges that are residual on each of the atoms. So what we want to do is we want to make sure that we have charges, like for example negative charges on very electronegative atoms and positive charges on very non-electronegative atoms. This is the bit that's in your notes for you. And then the next one gives you kind of like the key points, like I just said. Small numbers, preferably 0, are going to be helping with minimizing charge differentials between two close atoms on a Lewis structure. Make sure the bullet 4 is followed as well. The total numbers added together from the formal charges must equal, like for example, the polyatomic charge, like sulfate that we did, where we had our negatives and positives cancel each other out. In our first, not the best Lewis structure we drew for sulfate, but then we drew it again where we did double bonds with sulfur and oxygen, yielding 0, 0, 0, 0, and then 2 of the oxygens carried a -1 charge, summing at a -2, which is sulfate's charge. Okay, so I had some examples here for formal charge, but you guys will be practicing that a lot. So these are some extra practices where the Lewis structure is valid for all of these, but the best one is going to be based on the formal charge. So you guys can practice that if you want. And then I have some more here, but I think we're good with formal charge. Okay, resonance was the next thing we need to talk about. So write down what you need to here, but resonance is just basically you have two Lewis structures that are equally valid in terms of formal charge and everything, and the connections in which the atoms are connected can be altered. So essentially you might have a single bond between two atoms and a double bond between two other of the same atoms. So it was just your preference to put the single bond on one location and not the other, or the double on one location and not the other. So both of them are valid, but both of them are equally valid. So you have to kind of adjust for that. And this is called resonant structures. So you have two Lewis structures in which the connection, where the atoms are placed, is exactly the same. So you don't get to change atoms and atoms and atoms. Essentially what you're doing is you're changing the arrangement of the electrons, aka the bonds being single, double, and usually not triple. It's usually just single and double, but here we go. So what you want to do is between the two valid Lewis structures, you draw a double-headed arrow. For example, I'm going to scroll down a little bit more, like you see down here. The double-headed arrow represents that these two things are resonant structures, meaning they're equally likely. Though, neither of these actually occur. So you'll never find benzene that looks like this one right here, nor will you ever find benzene that it looks like this one, like right here. There is an intermediate between there that is the true structure of benzene, and these are all, of course, verified by things called like UV-vis spectra or IR spectra, mass spectroscopy. Lots of light-related tests are done to verify these. So a lot of times we'll draw the benzene like this with a single, double, single, double, single, double, but then you could equally draw it the other way, like noted here. But the true Lewis structure is actually called a superposition. Like pretend these two structures, structures number 1 and structures number 2, are superimposed on one another, but you can't draw double bonds everywhere because then we'd have more than octet, we wouldn't have the right number of valence electrons. So you have to write it either like this to show that these are equally likely, or this is the lazy man's way of drawing benzene, but this is saying that the double bond can be anywhere in here. I'll draw you another one in just a second for ozone, which is an alternate way of drawing the resonant structures here. So the important parts are none of these structures actually occur. There's instead an intermediate between the two structures that we have, or the number of Lewis structures that are possible here, that actually occur. And with that, the intermediate, there carries intermediate bond length and bond strength. So the bonds here between here and here. This is a double bond, this is a single bond. And same way here, double, single, single. But what actually occurs is a 1.5 bond. Sorry, that looks really bad, but I'm gonna keep it there. It's like a 1.5 bond. And so what you do is you just draw these dotted lines to say it's not quite a bond, but it's part of a bond. So each bond is 1.5 bonds. It's an intermediate between the length and the strength. So it's actually stronger than a single bond, but weaker than a true double bond. So intermediates between length and strength. And then this is a misconception as well. In the book, and sometimes even researchers will go, oh, the resonance structures flip back and forth between these two versions. Lies. No, it's an intermediate. It has its own special drawing and special Lewis structure. We just don't draw them very prettily like this one right here. Okay, for ozone, O3, you got 3 oxygens, so that's 6 times 3, so that's 18 valence electrons we have on our valid Lewis structure. So then we're going to draw oxygen in a line like this. So far I've used 4 electrons, and you guys can pause this and try it yourself before I continue. Pause. Okay, I'm back. So at this point I want to make sure that I have double bond, single bond. Let's fulfill this oxygen in the middle so it has octet. Octet, octet, octet. So how many have I used? 2, 4, 6, 8, 10, 12, 14, 16, 18. What? Got it? Okay, so 18. Now I just preferred to put it on that double bond on the left-hand side. I could have equally drawn it on the right side, meaning these two, and sometimes it's nice to put brackets around it to say that these are the 2 versions of the Lewis structure, though they equally do not exist. There's a superposition of them both on top of each other. Notice that this lone pair up here is going to cause some repulsion on the 2 side chains, so here and here, and that repulsiveness causes the atom to become bent. So I'm actually going to draw it like it's molecular geometry would look. Lone pair up here, electrons, electrons. Now it's hard to show octet on everything, but I'm actually going to try here. I'm going to put octet on this one on the right, and then what you do is like we did earlier, put a dashed line to say that that double bond could be on either of those sides, left or right. So this is kind of the combo resonance structure. Now it does not look as if this oxygen over here has octet, but we're going to assume it does because there's a double bond that potentially could be there. I think the best way to draw the Lewis structures and resonance is to show the double-headed arrow like this, and you will see this on the AP exam. So you guys can try carbonate, but resonance essentially is going to be very important in determining strength of bonds and length of bonds. So again, this does not have a single or a double bond. This has so that's wrong. We have a 1.5 bond, which has a bond strength greater than a single bond, but weaker than a double bond. That's the important part, is that you need to be able to verbalize that important point. Oh, so we're going to do an activity when we come back with the Born-Haber cycle. That'll be fun. Okay, so isomers we've heard of before, especially with organic chemistry, and you can see some organic functional groups here. So if you can remember to look on your Orgo functional group handout worksheet that I gave you, is like the 3rd page of the packet for this unit. You'll see some of those functional groups, for example, the alcohol group and the ether group. Remember, something is an ether if there's something on either side of it, haha. So alcohol, just remember the all OH group. Okay, so isomers are going to be the same exact chemical formula. So we have obviously C2, count up your H's, you should have 6 H's and 1 oxygen. That's the same formula for each of these, but we have a different arrangement of those atoms, so we have 2 totally different compounds, totally different. So that means that we have some physical properties and chemical properties that'll be different between these 2 because they are arranged in different ways. So we're going to talk about intermolecular forces and boiling point, melting point, things like that when we get to that. And these 2, ether and alcohols, will have different traits that are associated with them. But just know the definition of isomer. So speaking of isomers, let's go ahead and draw the Lewis structure for this guy, C2H4. So when you count up here, this is just because we need to draw some more and get some practice with this. C2H4, you have 2 times 4 electrons from carbon plus 4 from from hydrogen, So that's 8 plus 4. That's 12 valence electrons we have to work with. Carbon and carbon have to be attached to each other. As you can see here, in this one it's actually not, but that's because there's an oxygen. Oxygen will also usually be, it splits up carbons well because it can hold more than 2 electrons. You can't put hydrogen in the middle because that means you got to have it bonded twice, which would hold 4 electrons, and we know hydrogen's not good for that. So carbon-carbon have to be attached here, and then you have to have as symmetrical as possible, hydrogen and hydrogen. Okay, so far I've used 2, 4, 6, 8, 10 electrons. Those 10 electrons make up, most of my valences. I got 2 more to work with. But both carbon 1 and carbon 2 need another pair of electrons. So the only way to make that happen and not go over my valence count is to have a double bond here. So you've probably seen this before in your organic lectures. So there's our Lewis structure. There's no resonance here, actually. So we're just going to say there's a double bond between the carbon and carbon, and it's an ethene. So there's a couple different ways to see isomers. They're called constitutional or stereo. And so if I'm going to adjust this structure here in a second, just a quick reminder of cis and trans. I'm going to look at this example right here. If the two, this is a butene right here, butene structure, because we have 4 carbons on both of them. But if the carbon chain goes like on the same side, that has to be cis. If the carbon chain goes on opposite sides, that's a trans. So just don't forget that these are isomers because of the different arrangement of the atoms, meaning that the carbon chain follows a different route on the cis and trans structures. All right, so isomers down, resonance down. Let's do some molecular geometry. Oh, before we do that, this was a really interesting fact that we have to know about. If we have an odd number of valence electrons, how is that going to impact our structure, and how is it going to impact the reactivity of that structure? So one of the best examples of Lewis structures in which have odd number of electrons are things called free radicals. So you can read this here, but free radicals are things that attack your body. They attack your tissues. They oxidize your tissues. So we usually actually eat things that kind of counteract that. They're called antioxidants, like blueberries or anything with like a very dark pigment or have antioxidants in it, because we are constantly bombarded with these free radicals, specifically ones that are oxidizing our tissues and killing our cells. So free radicals are incredibly unstable. Unstable meaning very reactive. So if the reactivity is high, I'm not sure what over there, is high, that means it's going to try to steal another electron or give away its electron to another molecule. So we'll try to capture the needed electron to gain its own octet or its own stability. So it's going to try to steal its electron, or it can also donate or share. So when the attacked molecule loses its electron, it then has an odd number of electrons, which makes it the free radical. So the free radical is a chain reaction that's going to continually cause other molecules to then have odd number of electrons and make them very reactive, so on, so on, so on. This is incredibly important in environmental chemistry. Example, ozone destruction. And I have some images down here that you want to kind of take notes on and have a good example to go with this. So this is really important for some general knowledge. So the cascade effect of the chain reaction is eventually going to hopefully end when another free radical bonds with it, but it does a lot of damage along the way. So let's look at living tissues and then environmental chemistry here. So normal oxygen atom, 1 with 8 valence electrons. This one has lost electrons, so now it's a free radical. Free radicals are incredibly dangerous to your tissues, so you can see it happening in the cell membrane. The oxygens are going to keep going on and on and on. Now, this can be dangerous to your living tissues, but what if you have a cancerous tissue? It actually can attack cancerous tissues as well, aka tumors, and as it does that, it kills the propagating cancer cells so that they can no longer grow into the tumorous masses. So sometimes it can be used for benefit, but it has to be targeted, because if not, if you release these free radicals into your body, you're done. Okay, they're going to start killing tissues. So, for example, it's going to erode the cell membrane, but you can also neutralize these guys by taking antioxidants or eating foods that have antioxidant properties. Okay, so here's the environmental example over here. You can see that chlorofluorocarbons, CFCs, are going to be in the atmosphere. So you can see C carbon with 3 chlorines and a fluoride group up there. Whenever you have UV, which is UV is energy, strike those things, which should not be in our atmosphere, right? Those are coming from like hairsprays and air conditioners. Okay, so we really try to limit our CFCs that go into the atmosphere. Anyway, UV is naturally going to hit those whenever they are in the atmosphere. That breaks off one of the chlorines, and that chlorine is then going to essentially attack an ozone molecule in the upper atmosphere. Okay, that's bad because now we've lost our ozone layer, creating an ozone hole, because one little chlorine went and reacted with it. When it reacts, it makes diatomic oxygen, which is great for breathing, of course. Great for breathing, of course, but not great for the protection that we get from our ozone layer, okay? So that oxygen, diatomic oxygen, is going to be present, and then also we get the I guess, hypochlorite, that's not really a hypochlorite, it's just a chlorine bonded to an oxygen, that then can do that again with some other free oxygen molecule that was made. Okay, so as this happens again and again and again, this guy reacts, creating that free radical, the chloride or chlorine free radical. It's not actually a chloride, the chlorine free radical, which can then go on and chain react, causing more oxygen to be depleted. So a lot of times these free radicals are notated by the actual chemical symbol with a dot to show that it's got an odd number of electrons. You don't have to write them all, you just write one dot. So the environmental example is one that's incredibly important. And here's that again. You can see it. The chlorine is kind of like serving as the catalyst here for the destruction of ozone. So that's a prettier picture, I think, than the cartoon version. And then you might remember this example from kinetics, actually, because we have seen the 2 elementary steps here and what occurs. And then if you go through and cancel out the things that are common throughout here, you can see that that's serving as a catalyst. And then our intermediate is actually the chlorine here, so the intermediate. And as you add your 2 reactions together, you get a free radical, oxygen, reacting with ozone to make 2 oxygen diatomic molecules. So what you would need to do, in a kinetics example, you would know one of these is going to be the rate determining step. So let's say this one's the rate determining step and this one's a fast reaction. So you just need to know a little bit more information to apply that in kinetics. Okay, so I'm going to do a couple of expanded and exceptions to octet rule, but I think once you get the hang of it, you guys can go through these examples by yourself. But for those of you who are struggling still, listen through all of these examples. So beryllium and boron are going to have incomplete octet. Beryllium is really small. It's going to only get 4 valence electrons surrounding it. Boron is also very small. It's only usually going to get 6. And that's okay. You just have to understand how to do the geometries from that. So beryllium hydride. Beryllium has 2 valence electrons plus the 2 from hydrogen, so we have a total of 4 valence electrons. In the entire structure, beryllium's in the middle, hydrogen left and right. I'm done. I have used my 4 valence electrons as noted. This structure is definitely going to be linear because it's a left and right. There's no lone pairs pushing any bonds around to make some repulsive forces. Boron trifluoride here is going to be boron, which is 4 valence electrons, plus the 21 from total of 3 fluorines. So 21 plus that is 25. I just lied to you. This is 3 electrons. 24. I knew we didn't have an odd one here. Okay. 24 electrons total. So boron, and then you want to make these as symmetrical as possible. The bonding electrons need to be far away from each other. And then the fluorides get full octets. They are very electronegative, so they need full octet. Boron's okay. It's got less than that. It's also really small. So if you count them up, you should have 24. What you should notice is that boron has no lone pairs. That means that this is going to exist in one plane. One plane is a total of 360 degrees around, which means that these 3 ligands, however you want to say them, will be separated total 360, but each piece of the pie essentially is going to be 120 degrees apart. So that's a bond angle to know between fluorine and fluorine. Also, you should see that it's got 3 legs, so it's trigonal. trigonal, pyramidal or trigonal planar? Well, it's not a pyramid because there's no pushing up and down of these electrons from a lone pair, so it has to be planar. Trigonal planar. Expanded octet, so sulfur septafluoride, hexafluoride. Yeah, I was right, hexafluoride. I'm not sure what I'm saying here. And then xenon tetrafluoride. These are two really, really good examples because, like I said earlier, the expanded octets are going to come from anything with d orbital accessibility. So meaning like 3D, for example. If you can access 3D, you got extra pockets for those electrons. So those are going to be places that you can store them in order to form more bonds. And those bonds are going to be also covalent, so you're, some other atoms donating those electrons to you. So phosphorus, sulfur, chlorine, argon will commonly do expanded octet. So let's do one or two of these, and we'll do the bonds geometries with them. So sulfur has 6 valence electrons plus 6 times 7 for fluorine. Go ahead and pause this, try this yourself, and then check with me. It's 48 valence electrons, 48. All right, hopefully you paused that long enough to try yourself. You can speed this up if you have, and you can try with me. So we have 48 valence electrons. Sulfur must be in the middle. We have to have 6 attachments, 6 ligands, so F all the way around here. 2, 4, 6, 8. So far we've used 2, 4, 6, 8, 10, 12 valence electrons. And of course, fluorine is very electronegative. It does not like to share more than it needs to. So it's going to get octet via lone pairs around it the whole way. So we've used 48 electrons, and you'll see that sulfur has 12, so expanded octet, which is fine. So what these, and I'm going to go into more information on this one with the information regarding like the terminology you should use about where are these ligands or ligands located. So if you think about it, we have a large 3D area that we can accomplish this task. So we have sulfur that goes in the middle. We're going to have kind of a plane existing around it, and then we have the area above it and the area below it. So if you think about the Earth, we call the areas on the middle region the equator or equatorial region, and then the region that's going up and down on the y-axis is the axial region. So fluorines in this case are taking all positions here. There's one up top and down low, so there's 2 fluorine ligands on the axial axis, and then we have one fluorine here, 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 and here on the equatorial region. So this is actually going to take the shape of 2 pyramids butted up against each other, but we call that octahedral because there's 8 bases on both of those pyramids because they've got a square base, and if you draw like a kind of like think back to your geometry skills here. So you should see a pyramid up top with 4 faces, and then a pyramid down low to the back and to the back here with another 4 faces. So this is an octahedral drawing because there's 8 faces. Now, what are the bond angles here, though? The bond angles are actually pretty easy to see. If you think of something as a cross, and you can actually pretty much determine that everything here is going to be at a right angle to one another. So, for example, the angle between these fluorines, these fluorines, these fluorines, and these fluorines on the equatorial region, they essentially are forming a cross with each other. So that's 90 degrees right here. 90 degrees all the way around. So all those fluorines on the equatorial region are 90 degrees. Well, we also have a right angle between sulfur and the fluorines here from the axial region. So those are also 90 degrees. And I'm going to draw the one down low as well. This one's 90 degrees. So all of these bonds are at a 90-degree angle from one another. That one, octahedral, is actually really easy to remember. All right, so let's try this again. I'm going to go in a different color here for xenon tetrafluoride. Xenon tetrafluoride. We have xenon, a noble gas, which is okay with bonding because it's got a large mass and it's got a large number of energy levels to store additional electrons. So xenon plus 4 times 7, so 28 plus 8 is 36 valence electrons. So xenon obviously is going to be in the middle, and then we have fluorine, 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 fluorine. So we have 4 ligands with octet. So if you count them up again, we see around each of the fluorines are 8. So 8 times 4 is 32. So I've used 32 electrons so far. I have 4 more to put on someplace. Remember your rule for expanded octet? The central atom is going to be the one that is the largest and able to accommodate those extra electrons. So I'm going to draw them as 2 lone pairs on xenon. And for me, Miss Enlow, I sometimes can't see your dots. So please circle them or make them really prominent so I can understand that that Lewis structure is actually correct. So now you have to determine where in the heck are these extra lone pairs going to arrange themselves. Don't forget, key fact, lone pairs are extremely repulsive, okay? They will repel like nobody's business. So they need a lot of space to take up that around the molecule, around the central atom, so that they don't cause so much stress on those bonds and those bond angles. So lone pairs are going to take up the most space, and they try not to be too close to other bonded electrons, aka the bonds between xenon and fluorine. So we need to arrange that appropriately. So let's go back to the drawing board and let's think about the best arrangement. Xenon is going to be in the middle. Let's make our little plane around it. So I'm going to kind of spitball at you here. If we put a bonded pair here and make fluorine go here, and let's just guess here, and let's say we put a lone pair here. The lone pair is going to be at a 90-degree angle from fluorine. That is really, really close. Above 100 is best because that means it's farther away from the bonded pair. So I'm going to assume that that is too stressful and that molecule will not attain that shape. Therefore, that lone pair does not belong in the equatorial region. So let's erase this and not put the lone pair there. Okay, so let's go back and say, let's say no lone pair is equatorial because they're going to be 90, 90, 90 the whole way. Let's put fluorine each places, each corner. And then let's go and go, all right, well, is there another way to put the lone pair? Well, yeah, you can put a lone pair on top and a lone pair on bottom. Now, you're telling me, yeah, there's 90 all the way here too, Miss Enlow, so we got a problem. So this is actually the best way to put the lone pairs because there's a kind of a lose-lose situation here. You're going to be at 90 degrees everywhere, only due to the fact that we have to have that square base right there. So that's one way to go about it. We have 90 degrees here, 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 top, bottom, bottom. So we have 90, 90, 90, 90, 90 all the way again. So let's see if there's another way. So pause for a second and see if there's any other way you can think of here. Okay, so what you should realize is that there is no other way to put 6 total electron domains, which is what I'm going to call anything that is just a place where electrons live, so either a bonded electron domain or a lone pair electron domain. There's no other way to arrange these 6 total in a way that eliminates any more repulsion. But I will tell you there is a favorable Lewis structure here where the lone pair are axial. And it won't matter in terms of the bond angles or the bond stress, but the axial location allows you to see the shape of this molecule better. So if we are considering all electron domains, everything, you should see this very similar to sulfur hexafluoride. It should have an octahedral appearance to it when you look and you see those big balloon lone pairs, right? But what if you don't consider the lone pairs there? Maybe you consider them invisible. If you look at them invisible, or as invisible, then the shape you see is just based on the fluorines, and the fluorines there with xenon make a square. Well, that has a square planar appearance when you're only considering the molecular geometry, which is a consideration of atoms only. So atoms only, you should see a square planar figure here. But if you're considering everything, whole kit and caboodle, where you got all electron domains considered, meaning lone pair and atoms, it appears as if it is an octahedron. So we're going to talk about the differentiation between molecular geometry and electron group geometry in just a second. Okay, so these are some more. You should practice all of these. You will see some of these in the lab again. You'll see some of these in your test. You'll see some of these on the AP exam. So practice all of these so that you have good skills and that you kind of, at some point in time, you're going to start to see some weird shapes. Okay, so I will do one of these for you, or maybe two, so you have a good start. So I'm going to start with this one down here, chlorine trifluoride. So chlorine trifluoride has 7 plus 3 times 7, so that's 28 electrons. Fluorine is going to be in the middle, the singleton. Fluorine is going to be on each side. So far we've got 6 electrons used. Fluorine is extremely electronegative, so it gets all the octets off the bat here. So if you count around, say 7, 7, 7, that is 21 electrons. We have a bit more to use here. So if you put chlorine with the octet, I'm sorry, I lied. 8 is 24. Whew, I was like, what did I do here? Okay, 8 plus 8 plus 8 is 24. 24, now we've got 26, and then another lone pair of 2 electrons, which would be a 28. So don't forget, please make those very dark or circle them so I can see those. Now this one looks really similar to the xenon tetrafluoride, but we only have 3 true bonds that are here, so we've got some flexibility. So what happens here is we don't know the best way to arrange it. So let's try off with our normal, where you have kind of a triangle base here, where you'll have your fluorines, right? And so those are all equatorial. And then try out, and let's see, is there a way we can put lone pair here on top and lone pair here on bottom? Yes, there is. However, so that's on the axial region. However, these lone pairs are at a 90-degree angle with everything, with all these fluorines, and that's not cool, okay? Those are at 90 degrees. That's very close. So let's see if there's another way to morph this so the electron pairs have more space. Because look, you've got fluorines here. You know, we've got 360 degrees that we're working with in the equatorial region, and there's 3 bonds, so fluorine, 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 so they're actually 120 degrees apart, okay? So that means that, heck, I could put a lone pair there, and it would also be 120 degrees apart. So this is kind of a trial and error for you. Now, some of you guys are going to get it real fast and just understand how to do this, but I'm trying to give you some tools here. So let's try again. Chlorine, and let's put a fluorine up, another fluorine up, and then 1 fluorine to the side. And then I'm kind of showing you like a planar field here. And I'm going to put a lone pair, kind of dashing means I'm going into the board to the back. And then I'm going to put another lone pair here, which looks like it's coming out of the board. I know, my drawing skills are amazing. And you should see that as this. Fluorine in the middle, lone pair, fluorine, fluorine, fluorine. So these lone pairs should be 120 from this fluorine, 120 on the other side, and 120 between, okay? That is very favorable. Now, I do understand that with the fluorine on top and bottom, they are also 90. But in the previous example over here, the lone pairs were at 90 with every single fluorine, which is crazy stressful. So they are only at 120 they're at 90 and 120, which is a more favorable location. So this shape has a funny name here. So if you look at it just at the atoms, so atoms only, then you should see fluorine, fluorine, and fluorine, and this chlorine in the middle, of course. And that kind of looks like a T. So it's called T-shaped with atoms only. But if you consider every electron domain or every place where electrons exist, you should see a triangle with a top and a bottom. And I'm going to kind of sketch that out for you here. I'm missing one here, on to the back. So that's supposed to look like a trigonal bipyramidal. So trigonal bipyramidal, if you're counting all electron domains, and just T-shaped if you're considering atoms only. So this one is the top one up here is called the molecular geometry, and the bottom name that we have down here is called electron group geometry. So it's just two different names with different respects to the parts of the atom. Okay, so this is the reading guide too that you've already been successful with, I'm sure. Formal charge, drawing them, maybe some resonance structures if you looked ahead, okay? What you should be capable now on this one is writing down the molecular geometry for each. That means only atoms count, okay? And then you can also list the number of electron domains, which is just any kind of bond or lone pair. You will not be able to do hybridization yet, okay? We're going to do that later. And then try to explain resonance using one of the examples you have up here. And then do not try to draw the hybridized orbitals yet, because you don't even know what that is. Okay, so you stop here and you can do that. But I need to go ahead and talk about VSEPR, and then I'm going to draw every single molecular geometry possible, okay? So I'm going to pause and I'm going to do that and then talk through it. And that is going to be, that's already printed in your notes, and you need to just fill in the blanks. All right, so VSEPR, valence shell electron pair repulsion theory. We have been saying this and describing this the entire time we've been talking about Lewis structures and molecular geometry. So this is very familiar to you, but I just need to officially kind of tell you about VSEPR and the reasons behind our thoughts on the whole repulsion here. So and this is how we've been drawing them, so I think you'll be very familiar with this. The electrons are going to align themselves in a way that they are going to maximize their distance, because they are obviously two negatives near each other. It's going to repel, and repulsive forces are bad and stressful for the atom. They are too high energy, and we always want to make sure we have low energy, because the universe wants the rest, while the atoms and the chemicals have the least. So maximum distance, that means like 100 degrees and higher for their bond angle. This symbol here means bond angle. We want the biggest distance between them. And don't forget, lone pairs are going to be causing a lot of space to be taken up. So since they do tend to spread out, they also tend to repel bonded electrons, so the ones that are between two atoms. And so whenever that lone pair does its job of repelling, there's a change that occurs. There's a change in the geometry. So you must consider this lone pair doing its business of repelling before you know the geometry. Because like I said, anytime you have, like for example with water, those lone pairs, the reason we draw water as bent is because these lone pairs are doing some repelling, which causes this angle here to drop down to 104.5. So it was a tetrahedron, which was 109.5, but it drops down. Kind of looks like a happy face, actually. Okay, so that's going to affect the molecular geometry, the bond angles specifically. And then there's a good TED Ed video, which I'll have to show you guys later, but the TED Ed video you guys can look at from my notes, which talks about the reason behind VSEPR. It's pretty interesting if you have some time. Okay, so these are the electron pair geometries, and I'm going to go ahead and tell you these are the only ones that you will be listing if you ever are trying to do electron pair geometry. Because in this one, everything counts. Everything counts means that you're counting up lone pairs plus the bonds, which are areas in which electrons exist. So those are called electron domains. So a domain is just where it exists. So these are the only shapes you will write for these. And that's because you're respecting both lone pairs and the bonds. For the molecular geometries, you will see a lot more shapes listed and bond angles listed because of the new shape it takes on after the repulsion has occurred from the lone pairs, and then we look at that shape by itself. So these are going to be some molecular geometries you see. But I am going to go through and draw some of these for you. So take a look now. You'll see the bent one like we just said for water. You'll see some other weird ones called seesaw and T-shaped. And it's counting up atoms only and where they exist on the equatorial and axial planes. So I'm going to go ahead and draw these for you, but this is here for your information. I do not expect you to memorize this list of atoms bonded and lone pairs or positions or whatever. I expect you to be able to look at a molecule and do it. Memorization is not going to help. You have to understand this. So this is what I'm going to be taking some notes on. So I'm going to pause and do all this, and then I'm going to talk through it quickly. Alrighty, so you guys can copy down this information as I go. I'm just going to kind of give you a narrative of what I've written here. So whenever you have two electron domains, there's only one arrangement in which they can take, and that is linear, as you can see denoted here with 180 degrees apart. So a good example of that would be, like, for example, ozone. Oh no, not ozone. I lied. You guys can see the image here. Looking a little farther, we have 3 electron domains, so we've got another electron pair or we have another bond, and there's 2 scenarios in which that can take. The 2 scenarios are where you have 3 bonds and no lone pairs. The best arrangement for those bonds to be farthest apart are at 120 degrees apart from each other, because don't forget you have 360 degrees to work with. All of these will take place in the equatorial region. The equatorial region means that it will be a planar shape, because there's no up and down from that. It's just straight, it's a flat shape. So that's called planar. It's specifically trigonal planar due to the fact that it is a triangle, 3 legs there, 3 ligands. The other arrangement it can take is if you have one lone pair. That one lone pair does some repelling of the bonded pairs here, and those bonded pairs, when they are repelled, they have to squish together. So everything was 120 apart, like trigonal planar shape was though. So this big, huge electron pair, lone pair, will do some repelling, causing this angle here to become a little closer together. And closer together means less than 120. We don't always know exactly what it is, so sometimes you're allowed to say less than. And there's another word for this shape. We usually would just call it bent, because if you're looking from here down here, it looks bent, like water looks bent. But another older term for that is angular, because it looks like an angle. So just know both of those terms. If you gain another electron domain, so another either lone pair or bond, you have quite a few shapes you can take on. The one that we know best is tetrahedral. So this is 4 bonds, no lone pairs. No lone pairs. Tetrahedral has a 3D shape, so it takes up area in both the kind of equatorial and axial region. It just doesn't align that way. So the bond angle here is very important to know. So from this to this, you can definitely see it's not a right angle, so not 90 degrees, it's 109.5. We've gone over this already, and that's called tetrahedral, 4 legs, tetra. If you have 3 bonds, or ligands, and you have 1 lone pair, that 1 lone pair is going to repel the other bonded areas. So it's repelling here, here, and here, causing that previously tetrahedral shape, which was 109.5, to take on something less than 109.5. We know that to go down 2.5 degrees, so that's 107 degrees. And sometimes it's okay to say less than 109.5, because it's not always exactly 107. It can be a little less or a little more based on how large the atoms are and how close together they can get, especially hydrogen's so close, so it can move down quite a bit. That shape appears as if it's a pyramid. That pyramid shape is denoted as trigonal planar, because there's 3 legs on the pyramid. If you go down one more, you have 2 lone pairs and 2 ligands, then you now have to accomplish more repelling of the bonded bonds here, the bonded pairs. So that causes the angle to be doubly smaller, so there's 2 little inequality signs here, and that's actually water we know is 104.5, so if you say extremely less than 109.5 or something like that, you should be okay, but 104.5 is pretty impressive to know, especially on the AP exam. So that shape is definitely bent because of the angular shape here taken by the atoms. So remember, molecular geometry is concerned about what do the atoms look like after the repulsion has occurred. The atoms only. Don't even look at the lone pairs after you've decided on how they repelled. The last and final shape, I'll say, is kind of weird. You've got 3 lone pairs and 1 lone pair and 1 ligand, kind of. And so I actually gave you an example over here, hydrofluoric acid. So around this one you've got 3 lone pairs, but still the shape here is just a straight line between the 2 atoms, so therefore it's linear, and you can see the 180 difference. These are the big bad ones. These are the ones that are going to be a little bit more funky in the bond angles, so these you have to really pay attention to. If you have 5 electron domains, so 5 bonds or a mixture of bonds and lone pairs, you've got some complex 3D structures. So the first one is going to be when you have 5 actual bonds, the best way for them to arrange themselves is for some to take the equatorial region and some to take the axial region. There's only two directions in axial, up and down. So 2 of them take that position, leaving 3 in the equatorial position. Those 3 in the equatorial position are 120 degrees apart. And then the axial region from a x plane to a y plane is definitely only 90 degrees. Now, if you look at this one closely, I've kind of started the drawing over here. It takes on a trigonal bipyramidal, 2 pyramids, bipyramidal shape. So it has 2 angles that you must know, 120 and 90. Let's drop down one, I love this shape, drop down one bond and add 1 lone pair, and you get this shape called seesaw. Now, I will have to show you this one in class because it's hard to see on a 2D image from the board, but I tried to draw it, okay? So this seesaw shape occurs because if you laid this one flat on its side, it would rotate up and down like a seesaw. So 2 bonds will take the axial region, 2 will take the equatorial, because why would you put all 3 in the equatorial if you got space up and down as well? Because the lone pair is going to prefers the equatorial here, because the equatorial yields 120 degrees apart from each other if you have 3 things in the equatorial space. So 3 things, 360 divided by 3 things is 120. So lone pair must take that spot. Well, essentially what you have is like a little guy with 2 arms sticking outward at 120 degrees from each other. So if these are those 2 guys at 120 degrees from each other, if you lay them flat on the ground, the 2 axial ones kind of appear as if they're at a slant, and you can actually make it slant the other way, and those 2 are still down here on the ground. So look, it looks like it's seesawing back and forth. Of course, your x and y axis are at 90 degrees from each other. So you've got 120 and 90 there. All right, so we go down one more lone pair in the picture, 1 less bond or ligand in the picture. This one is the one we talked about earlier with the chlorine trifluoride, and it's where your 2 lone pairs want the most space possible. The most space possible, when you have a limited number of ligands, by the way, is in the equatorial regions. The equatorial region here and here gives them space, and those are at 120 degrees from each other. So that is the only reason the lone pairs prefer equatorial in this scenario. The ligands that are top and bottom from one another are at 90 degrees from one another. That's what you need to know, because we're actually in molecular geometry, we're concerned about where the atoms are located. And, you know, we have to know what the electron pairs do, but where the atoms are located are bonds to know. So that's why this one only says 90 right here. So this is, if you look at it, turn your head sideways, it looks like a T, like that. So that one's called T-shaped. Drop one more bond and attain one more lone pair. Now, the lone pairs we're not going to go axial yet, because they would be at 90 degrees from other things, and that's unfavorable. So in their best interest is they will still maintain the equatorial region. Equatorial region here in the middle still yields lone pairs 120 degrees from each other. The lone pairs are at 90 degrees from the axial stuff, bonds, but they're still 120 from each other, so we're doing good. And you guys will mess with this in the lab a lot. After that, though, when you consider only the atoms from X to X, they are 180 degrees from each other. So it is a linear appearance. All right, last and final, we get down to the most complex ones, the 6 electron domains, meaning we have 6 bonds or a combination of 6 bonds and lone pairs. This one is the octahedral one, sulfur hexafluoride we talked of previously. So we have 6 locations in which bonds have to point. Well, we have 4 possible locations in the equatorial region. We have 1 up and 1 down. So everything here is in a square. Everything here is at a right angle to one another, so it's 90 degrees all the way. And if you look at it, it's 2 square pyramids on top of each other, but that's still called octahedral. Going down one, we go 5 ligands and 1 lone pair. That 1 lone pair has to take the axial position. I know I say axial, if you turn it sideways it looks like it's equatorial. I'm just telling you to put it on the bottom or top in the way that you picture in your mind or on paper the 3D image here. So in this big massive electron shape, we've got the lone pairs preferring the axial, and you'll see that continuing down to the next example. But if you're looking at the picture and ignoring the lone pair shape, or the lone pair, this looks like a, oops, looks kind of like a square pyramid. So pyramidal because it's got the point on the top, square because it's got a square base. And those are still all at 90 to one another because we are taking at the X, Y, and Z axis. All right, drop one more ligand. So we only have 4 ligands and 2 lone pairs. Those 2 lone pairs need to be as far apart from each other as possible. Far apart means one takes top, one takes bottom, and they're done. So lone pairs are preferring the axial here. Then if you look at your shape, this was our xenon tetrafluoride. This was a square planar shape because there was no point from the pyramid. So there's no pyramid here from an atomics perspective, only a lone pair perspective. So for the molecular geometry, this one is called square planar. But if you do consider the lone pairs, the electron group geometry would be octahedral. Woo, doggies, that was a lot of molecular geometry. You guys are going to be building some of these in the lab on Monday and mastering your skills. The last thing we need to talk about is polarity. So if you want to pause and come back to this one will be very short. Bond polarity, this is something you're familiar with from Honors Chem. We have 2 versions of this. You'll either be nonpolar or you'll be polar. That's just the bond. So now we're narrowing down to just a single bond between 2 atoms. A single bond between 2 atoms, when it's in a shared space, is going to be considered a covalent bond. Covalent bonds are usually bonds between 2 nonmetals. Those 2 nonmetals will have differences in their electronegativity. If their electronegativity difference is very, very, very much the same or very small difference, so essentially they have equal sharing here, that's a nonpolar bond. And notice I'm saying nonpolar bond. I could go nonpolar covalent bond to get really specific because it's a covalent bond still. But I'm not saying nonpolar atom, molecule, nothing. I'm saying nonpolar bond. You have to say to me the covalent part of that. Okay. And then if you have a large difference in the electronegativity difference, then it's going to be considered a polar bond because you have opposite ends of the bond. You have electron density way more, and this is from our video from the crash course one. You have a high amount of electron density on one side of the bond, and you have low electron density on the other side of the bond, meaning one side is partially negative and the other side is partially positive. So opposite ends here means polar. And that's where we have a dipole moment. We usually will indicate by writing above the bond, if it's asked for, of course, above the bond or below the bond, an arrow with a hash mark on the positive side because it kind of looks like a positive, and then an arrow pointing towards the negative region. So see the differences here between the electron clouds, same. So we have a nonpolar covalent bond. We have 2 different ends, so not a polar covalent bond. And then the ionic bond, it means there's no bond actually, it's just an electrostatic attraction, where we have a full positive on one side and a full negative, just because the electrons have donated themselves to each other. This last image just shows you the change, how it's in the middle, how it lies to one side to indicate the dipole moment. So, like I said, they have a difference in their electronegativity. So, we have some general rules. If their difference is small, between 0 and 0.5, it's nonpolar covalent. If it's somewhat large, so between 0.5 and 1.7, and there's a continuum here, so that means that we're going to say it's more polar than not polar. So this is a nonpolar covalent, this is a polar covalent. And if there's a humongous difference here, so above 1.7, it's generally going to be ionic. But how can you know for sure it's ionic? It's probably between a metal and a non-metal, a bond between a metal and a non-metal. This highlighted yellow part is probably one of the most important key facts you may not remember from Honors Chem. If your difference between electronegativity is very large, that means the bond between you, So, for example, H and Cl. H has a stronger attraction for Cl than H has for another H. So the bond is stronger between this polar, the difference in electronegativity, because it just means that they attract each other more because they have partial positives and partial negatives, versus something that's even stronger than that, like NaCl, because their electronegativity difference is huge, which makes them two ions, which they have full charge differences. And this all relates back to Coulomb's law. So sometimes you'll have to explain something via ionic character or covalent character. Just means that they're more on the ionic side of the continuum versus the covalent side of the continuum. All right, so that's just the bonds, just the little space between two atoms. Now, if you have to consider the entire molecule, the whole shebang, every lone pair, every bond, the position in which they are located, meaning you already know the molecular geometry of it, then and there is when you can determine the molecular polarity. So that's the polarity, or the differences in where the electrons exist on an entire molecule. So some molecules are going to have a region where there's a lack of electrons, and a region where there's an excess of electrons. That just means it's polar because there's a difference in electron distribution. It's unequal. So a polar molecule has a center of positive charge and a center of negative charge just because the electrons are distributed unequally. The whole entire molecule can be said to have a dipolar, or it is dipolar. It has an entire dipole moment over the whole shebang. So for example, water, we already know is polar. That's not a secret. I'm not spilling the beans here. Water is polar. And that's because we said there's an electron area up top that's slightly negative, on the top north side of the molecule. On the bottom side is slight positive, slight, by the way, because of the lack of electrons. This whole molecule has a whole dipole moment pointing upward, straight through it, okay? So I'm not drawing it on a specific bond. I'm drawing it on the molecule. The molecule's dipole moment is a function of two things: shape, geometry, distribution of electrons. Don't worry about this formula at all right here, but sometimes you'll see something has a unit of Debye's. Debye units are the dipole force unit. So this is just another image to indicate the same thing. We have, I call these the rainbow models because they're rainbows. So if you have something with a large electronegativity difference, and this one's a linear structure, so we have hydrofluoric, hydrochloric, hydrobromic, hydroiodic acid. There's a large difference in their electronegativity, so their polarity is increasing to this direction, okay? So we have dipole moments pointing this way, a slightly smaller dipole moment pointing this way, a really slightly smaller dipole moment pointing this way. These arrows are getting smaller. I don't know if you can tell that. And then this one has an extremely small dipole moment as a whole because it's smaller electronegativity differences. So this one is the most polar. Hydrofluoric is the most polar, having a dipole moment of 1.82, and then on down, you can see the dipole moments decrease this way. Their electronegativity decreases, but inversely related is their bond length. So the most polar means that they're most attracted, meaning their bond length is smaller. So know that bond length is inversely related to either the electronegativity difference or the dipole moment. All right, so in the considering time, I'm going to let you guys read this, but I do want to talk about one example. So bonds can be polar, bonds can be nonpolar. Molecules can be polar, molecules can be nonpolar, but there's a reason we have to talk about molecular polarity after molecular geometry, is because the geometry does matter. So if you can cancel two dipole moments because the geometry allows for it, we've canceled them. That means the geometry is, that means the polarity is nothing. It's nonpolar. So if I draw carbon dioxide itself, the C to O bond, it's got some electronegativity differences here. So I'm going to draw the bond having an electronegativity difference pointing toward the oxygen because it's more electronegative. but actually to draw the molecular structure. We would say 4 plus 2 times oxygen, 6 each, so that's what, 12, 16. We have 16 electrons here. Carbon is in the middle, oxygen is on either side, and then we have to accomplish 16 electrons. So I already know, and you may as well, you also may know, this has 2 double bonds. 2, 4, 6, 8, 10, 12, 14, 16, 16. Okay, this shape is linear. So our geometry is important here because if you go and go, all right, I know that carbon is less electronegative. So there's a dipole on this bond right here pointing to the right. There's also a dipole moment pointing towards the left. These dipole moments are the exact same size because they are the same difference in electronegativity between the C and the O's on left and right. So these two dipole moments pointing in opposite directions cause them to cancel, which means that the whole entire molecule is nonpolar because there's no left or right that's has more electrons than the other side. Left or right have the same number of electrons, same distribution of electrons around the molecule. We say that they're equal, so nonpolar overall. So that's called a nonpolar molecule. So weird, right? You have polar covalent bonds, which with the molecular geometry cause a nonpolar molecule. So you have to be able to relate the bond polarity to the molecular geometry in order to get the molecular polarity. So you guys can try these to indicate if the total molecule is polar or not. There's some additional examples for the linear ones. The trigonal planars, if they are all the same exact bonds here. So let's say boron trifluoride, of course with all the electrons, that would be considered equal, equal, equal. The dipoles would cancel each other out. I do know that they are not exactly opposite from one another, but they're pulling electrons to the circumference of the circle or the perimeter of the circle here, so we are assuming that they are canceling each other out. Tetrahedral will do the same thing. Even though they're not exactly opposites from one another, they can pull electrons up, to the right, back, and forward equally. So for example, methane, when you draw it, it will have 100% cancellation of dipole moments, so overall nonpolar. This one, however, bent, aka water, H's, oops, that looks like an H, right? H. And then those are definitely going to have a overall dipole moment pointing that way. That's supposed to be a bond. So dipole moment definitely is there, so cancellation does not occur. Okay, so you guys can try these. We will practice some of these together. I really appreciate you watching this video, and have a lovely day.